Hi everyone, welcome back to another video in our Ethereum series. In this video, we'll take a deeper look into accounts on Ethereum. So, account is an entity with an Ether balance that can send transactions on Ethereum. There are two types of account, externally owned account or EOAs or contract account. EOAs are controlled by anyone with the private keys, and a contract account is a smart contract deployed on the network and it is controlled by code. Now, both of these type of accounts can send, receive, and hold Ether and other tokens, and they can also interact with the deployed smart contracts. That is, EOAs and smart contracts both can interact with other smart contracts. So, if we look at the major differences between EOAs and smart contracts, it comes across four factors. First is account creation cost. You can create an externally owned account for zero fee. While when you deploy a smart contract, you have to pay some fee because code is being stored in the network storage. And since you are using network's resources, you have to pay for that accordingly. When it comes to transactions, EOAs can initiate new transactions, while smart contracts can only send transaction in response to receiving a transaction. So, as an end user, you can create a new transaction to any smart contract, but a smart contract cannot create a new transaction by itself, which is good. Otherwise, Skynet would have just been around the corner. So, a smart contract cannot really initiate a transaction by itself, but they can initiate a transaction in response to receiving a transaction from the user. So, if you send a transaction to a smart contract and it needs to interact with some other smart contracts to get the job done, then it will create a message call kind of thing that would forward your instructions to the second smart contract. The third difference is in interactions. The transactions between two EOAs can only be ETH or token transfers, while the transactions from an external account to a contract account can trigger code which can execute many different actions, such as transferring tokens or even creating a new contract. So I think this is very simple and obvious that as an end user, if you are interacting with another end user, you can only send tokens or ETH to them, or you can receive Ether or tokens from them. There's not really much that an end user can do with another end user. But when an end user is interacting with a smart contract, the smart contract code can execute many actions based on the logic of the contract, the problem that it's trying to solve, and it could end up resulting in a transfer of tokens or creating a new contract or interacting with multiple contracts to get some kind of job done. So you have a broader scope of interactions when it comes to end user accounts and smart contracts, and also between smart contracts. The last difference is in private keys. So EOA has public private key pair for controlling the account activity. The end user would generally have a private key out of which the public key would have been derived. And that private key is used to control all of the activities related to that public key. That public key is basically the end user account on blockchain. But on the other hand, with smart contracts, you don't have private keys. Smart contracts are controlled by the logic of the code that is stored in them. Talking about the constituents of an account, there are four things: nonce, balance, code hash, and storage root. So, any account on Ethereum would have these four things. Nonce is a counter or a number. For EOAs, this is the number of transactions sent by that account. So let's say if you have an account and you have already made 20 transactions, the nonce value would denote that you have already made 20 transactions. This is generally useful for protecting against replay attacks, where you cannot mimic a similar transaction twice. For contracts, the nonce value is the number of contracts created by a contract. If you recall from our previous part, Solidity Basics, we covered a concept called contract factory, where one contract can create multiple contracts. So when that happens, the number of contracts created by a contract is stored as the nonce value. Balance. A balance is the number of way held by an address. It could be either an EOA or a contract. It would ultimately be holding some ether. and that value is denominated in way and stored in the field balance. Code hash. Code hash is the code of an account on EVM. It's the only immutable field in the account. The nonce keeps changing based on activity. The balance keeps changing based on activity. The storage hash also keeps changing based on activity. But code remains immutable. If you recall from our video about dApps, the major drawback of dApps is that they are immutable and they are very hard to maintain, because once you have deployed a code on the smart contract, it's immutable. You cannot really change it. For EOAs, the code hash is the hash of an empty string, but for contracts, it is the hash of the code, that is the Solidity or the Viper code that you have written, that is converted into raw byte code, and the actual byte code is stored in the state database. So that entire code is hashed, and the hash of that code is stored in the code hash field for smart contracts. The last field, storage hash, also known as storage root, contains a 256-bit hash of the root node of a Merkle Patricia tree that encodes the storage contents of the account. This tree encodes the hash of the storage contents of this account. So all of the data associated with an account is stored in a data structure called Merkle Patricia tree on Ethereum. It's a data structure where you have the data stored in the leaf nodes, and it is hashed in the form of a tree, and the root of the tree is stored as storage hash. An EOA account on Ethereum is made up of a cryptographic pair of keys called public and private keys. So you actually hold a private key from which you can access the public key on the network, which is basically your account. So any activity that you do from your account would actually be an activity done by your public key, which was derived from a private key. And this private key is necessary for signing the transactions whenever you are creating a transaction request. So this key pair, these two keys together, help prove that a transaction was actually signed by the sender and prevent forgeries. Now let's check out the accounts on Etherscan. We'll refer a transaction that we referred in one of our earlier videos. You can see that a transaction happened from one account to a smart contract, and when you'll go to when you'll go to the profile of these accounts, you'll see that this is an account address and it is denoted as address here. So this is a normal EOA, an externally owned account by a user who is doing some kind of transactions here. So you can see the balance here and all of the transaction history here. On the other side of the transaction, we have the smart contract. So whenever you are viewing a contract account, you'll see the contract written here. And again, this has its own balance. One difference from EOA is that the contract account has a smart contract code stored in it. So you can access that here in the contracts tab, and you can actually see the code stored in the smart contract. So that was all that you needed to know about accounts on Ethereum. Now the question arises, how are these accounts created? So for EOAs, whenever you want to create an account, most libraries will generate a random private key for you. A private key is made up of 64 hex characters, and it can be encrypted with a password. So if you recall creating a MetaMask wallet, you have to enter password, and then your private key is created and a seed phrase is generated. So that seed phrase is nothing but a human readable representation of this private key that was generated for you, and it uses a hash based dictionary. It divides the private keys into multiple chunks and uses those values on a hash table to come up with words, and that makes the seed phrase a much more readable form of the private key. The public key is generated from the private key using an ECDSA algorithm, also known as elliptic curve digital signature algorithm. You get a public address for your account by taking the last 20 bytes of the Kachak 256 hash of the public key and adding a 0x to the beginning. So this is an example of an EOA address, and you'll see it everywhere on the Etherscan or on your MetaMask wallet wherever your accounts are listed. Now, it is possible to derive new public keys from a private key, but you cannot derive a private key from the public keys. That is what makes these applications more secure to use, because the private key would stay with you and you have to be cautious that you don't lose your private key. But since the private key is only with you, so only you can access your account and nobody else can do any kind of activity from your account, because ultimately to do any kind of activity on the blockchain from your public key, you have to sign the transaction request using your private key. The contract accounts also have a 42 character hexadecimal address. They look something like this. It's similar to the public key of an EOA, but the contract address is usually given when a contract is deployed on the Ethereum blockchain. So whenever you write a Solidity code and deploy it on the Ethereum blockchain as a smart contract, its address is generated when it gets added as a smart contract on the network, and the address comes from the creator's address and the number of transactions sent from that address. Like if you are deploying a smart contract, so your public key will be used and the number of transactions that you have done from that public key. These two things are used to derive the address of the smart contract. We also have validator keys. These are BLS keys and they are used to identify validators. These keys can be efficiently aggregated to reduce the bandwidth required for the network to come to consensus. So, when the process of consensus happens, all of these validators who are validating and verifying the transactions, they communicate with each other to arrive at a consensus whether the transactions are valid or not. And there's a lot of back and forth going on, a lot of network activity going on. So all of these validators have some data, they sign it with their own keys and send it to other validator nodes. So a lot of network activity is happening. And BLS keys are special kind of keys that makes this network activity more efficient. So without this key, the internode communication would have costed a lot to the network. The last thing that you need to know about accounts is wallet. So an account is not really a wallet. An account is a key pair for a user owned Ethereum account. On the other hand, a wallet is an interface or an application that lets you interact with your Ethereum account. You might have come across examples like MetaMask, Phantom, Coinbase Wallet, etc. So the idea is that you have a public key on Ethereum that does all of the activity, and there's a private key associated with that public key that would be kept by you, and you can only make transactions using the particular public key. The wallet is just a user interface that makes that entire process much more easier for you. Like you can create multiple accounts on MetaMask, so all of that are derived from a single private key. You can switch accounts using a drop down, you can make transactions easily, you can sign transactions, you can set gas fee, etc, etc. So wallet is more of an application and it's not really an account on Ethereum. So that was all about accounts for us, and in the next video we'll cover transactions.